The last ingredient we need is this layer here, the linear layer. So as you remember from my slides, the output of the multi-head attention is something that is sequenced by D model. So here we expect to have the output to be sequenced by D model if we don't consider the batch dimension. However, we want to map these words into the back into the vocabulary. So that's why we need this linear layer, which will convert the embedding into a position of the vocabulary. I will call this layer called the projection layer because it's projecting the embedding into the vocabulary. Let's go build it. What we need for this layer is the D model. So the D model, which is an integer, and the vocabulary size. This is basically a linear layer that is converting from D model to vocabulary size. So dot projection layer is let's define the forward method. Okay, what we want to do, let me write a little comment. We want to batch sequence length to D model converted into batch sequence length vocabulary size. And in this case, we will also already apply the softmax, and actually we will apply the log softmax for numerical stability, like I showed before. To the last dimension. And that's it. This is our projection layer. Now we have all the ingredients we need for the transformer, so let's define our transformer block. In a transformer we have an encoder, which is our encoder. We have a decoder, which is our decoder. We have a source embedding. Why we need the source embedding and the target embedding? Because we are dealing with multiple languages. So we have one input embedding for the source language and one input embedding for the target language. And we have the target embedding. Then we have the source position and the target position. Which will be the same actually. And then we have the projection layer. We just save this. Now we define three methods, one to encode, one to decode, and one to project. We will apply them in succession. Why we don't just build one forward method? Because as we will see, during inferencing we can reuse the output of the encoder. We don't need to calculate it every time. And also we prefer to keep these outputs separate also for visualizing the attention. So for the encoder, we have the source of the, because we have the source language and the source mass. So what we do is we apply first the embedding. Then we apply the positional encoding. And finally, we apply the encoder. Then we define the decode method, which takes the encoder output, which is the tensor, the source mask, which is the tensor, the target, and the target mask. Oops. And what we do is target. We first apply the target embedding to the target sentence. Then we apply the positional encoding to the target sentence. And finally we decode. This is basically the method, the forward method of this decoder. So we have the same order of parameters. Yes. Finally, we define the project method, in which we just apply the projection. So we take from the embedding to the vocabulary size. Okay. This is also the last block we had to build, but we didn't make a method to combine all these blocks together. So we built many blocks. We need one that, given the hyperparameters of the transformer, builds for us one single transformer, initializing all the encoder, decoder, the embeddings, etc. So let's build this function. Let's call it build transformer. That, given all the hyperparameters, will build the transformer for us, and also initialize the parameters with some initial values. What we need to define a transformer? For sure, in this case, we are talking about translation. Okay, this model that we are building, we will be using for translation, but you can use it for any task. So the naming I'm using are basically the ones used in the translation task. Later you can change the naming, but the structure is the same, so you can use it for any other task for which the transformer is applicable. So the first thing we need is the vocabulary size of the source and the target, because we need to build the embedding, because the embedding need to convert from the token of the vocabulary into a vector of size 512. So it needs to know how big is the vocabulary. So how many vectors it needs to create. Then the target, which is also an integer. Then we need to tell him what is the source sequence length and the target sequence length. This is very important. They could also be the same. In our case, it will be the same, but they can also be different. For example, in case you are using the transformer that is dealing with two very different languages, for example, for translation, in which the tokens needed for the source language are much higher or much lower than the other one, so you don't need to keep the same length. You can use different lengths. The next hyperparameter is the D model, which we initialize with 512 because we want to keep the same values as the paper. Then we define the hyperparameter n, which is the number of layers, so the number of encoder blocks and the number of decoder blocks that we will be using is, according to the paper, is 6. Then we define the hyperparameter h, which is the number of heads we want, and according to the paper it is 8. The dropout is 0.1. And finally, we have the hidden layer, DFF of the feed forward layer, which is 2048, as we saw before on the paper. And this builds a transformer. Okay, so first we do is we create the embedding layers. So source embedding. Then the target embedding, then we create the positional encoding layers, We don't need to create two positional encoding layers because actually they do the same job. They also don't add any parameter, but because they have the dropout, and also because I want to make it verbal so you can understand each part without making any optimization. I think actually it's fine, because this is for educational purpose. So I don't want to optimize the code. I want to make it as much comprehensible as possible. So I do every part I need. I don't take shortcuts. And then we created the encoder blocks. We have n of them, so let's define. Let's create an empty array. So we have n of them. So each encoder block has a self-attention. So encoder self-attention, which is a multi-head attention block. The multi-head attention requires the D model, the H, and the dropout value. Then we have a feed forward block. As you can see, also the names I'm using are quite long, mostly because I want to make it as comprehensible as possible for everyone. So each encoder block is made of a self-attention and a feed forward. And finally we tell him how much is the dropout. Finally we add this encoder block. And then we can create the decoder blocks. We also have the cross attention for the decoder block. We also have the feed forward, just like the encoder. Then we define the decoder block itself, which is decoder block. Cross attention, and finally the feed forward and the dropout. And finally we save it in its array. We now can create the encoder and the decoder. We give him all his blocks, which are n, and then also the decoder. And we create the projection layer. Which will convert the model into vocabulary size. Which vocabulary? Of course the target, because we want to take from the source language to the target language, so we want to project our output into the target vocabulary. And then we build the transformer. What does it need? It needs an encoder, a decoder, source embedding, target embedding, then in source positional encoding, target positional encoding, and finally the projection layer. And that's it. Now we can just initialize the parameters using the Xavier uniform. This is a way to initialize the parameters to make the training faster, so they don't just start with random values. And there are many algorithms to do it. I saw many implementations using Xavier, so I think it's a quite good start for the model to learn from. And finally, we return our beloved transformer. And this is it. This is how you build the model. And now that we have built the model, we will go further to use it. So we will first have a look at the dataset, then we will build the training loop. After the training loop, we will also build the inferencing part and the code for visualizing the attention. So hold on and take some coffee, take some tea, because it's gonna be a little long, but it's gonna be worth it. Now that we have built the code for the model, our next step is to build the training code. But before we do that, let's recheck the code, because we may have some typos. I actually already made this check, and there are few mistakes in the code. I compared the old with the new one. It is very minor problems, so we wrote feed forward instead of feed forward here, and so the same problem is also present in every reference to feed forward, and also here when we are building the decoder block. And the other problem is that here when we build the decoder block, we just wrote nn.module. Instead it should be nn.module list. And then the feed forward should be also fixed here and here in the build transformer method. Now I can delete the old one, so we don't need it anymore. Let me check the model. It's the correct one with feed forward. Yes. Okay. Our